Okay, sorry for the delay. So today we're going to have the second class on OWL, on the web ontology language. So we're going to dive a little bit into how to define these languages. Yeah, so how we formally define them. So the last time we spoke about the language itself, and we spoke about family relations and OWL using this Godfather example. So today's topic, we're going to talk a little bit about how to define the meaning of these ontologies, what kinds of reasoning tasks, what kinds of things we can do with these ontologies, what kinds of tasks we can define. So we're going to try to capture the main ideas of OWL. So here we see OWL according to the standard, and here we see OWL according to this class. We're going to capture the main ideas. There's going to be some details that I'm going to talk about at a little higher level. As we can see here, it's not a bad approximation. It's more or less similar-ish. Okay. So yeah, and we're also going to talk about more conceptual issues. So some of the stuff that we're going to talk about today is a little bit more conceptual. It's a postgrad course. We're going to get into some more theory topics, but hopefully not too heavy. Hopefully it's understandable. Okay, so we have to define this language. If we want to use ontologies in applications like biomedicine or in hospitals or in law and so forth, where these ontologies are being used, we need to be precise about what they mean. So we need to formally define the meaning of this OWL ontology language. And the question is, how can we do that, right? So how can we formally define what this means? So the last time we saw this one-of example, one-of is one of the features of OWL. Let me put this over here, maybe better. Where we have Godfather is equivalent class OWL, one of Vito, Michael, and Vincent. Yeah? And the question is, how can we formally define what this means? So one way we could think about doing it, as we saw in RDFS, we can think about defining rules. So we could say, okay, if these premises hold, then we can conclude something like this. So what does this say? It says that if C is an equivalent class of one of x1 to xn, then we can say that x1 is of type C, x to xn is of type C, something like that. Yeah, so we could have a rule that says all of these people here then must be Godfather. Yeah. So we get this type of inference based on this rule here. But that doesn't really capture the meaning of what this definition or this axiom is saying. What this axiom is saying is that they're equivalent. Yeah, so it's not just things go in this direction, but we can also use information if we know that someone is a Godfather. We can also use some information, we gain some information in the other direction. Yeah. So if we know, for example, that Vito Young is a Godfather, what can we conclude from this? Must be one of the others. Yeah, so it must be Vito or Michael or Vincent, right? So which one? We don't actually know. We're not sure yet. Yeah. However, if we knew that Vito Young was different from Michael, different from Vincent, and was a Godfather, what could we conclude? Must be Vito. Yeah, must be the same as Vito. Yeah. So we ruled out all the other possibilities. So in this way, we could again think about trying to define a rule for this case. We could try to define a rule that if someone is an instance of a class that's equivalent to a one-of, and we know it's different from all but one of the elements of the one-of, then it must be the same as. So we have some sort of rule like this, but it's quite difficult. It's becoming difficult to write this rule. We have to somehow use multiple rules to capture that it might be any element of the list and so forth. And still, this is a very specific rule. It's not capturing exactly the semantics as we'd like to define it. So what is, if it's not the first element in this rule here, sorry, we define that as if it's the first element, that's same as the first element here. We could define that with multiple rules and so forth, but it gets a bit more difficult. And we'll still not capture all of the possible cases or the real meaning behind this particular feature. So the difficult thing to capture in this feature here is the disjunction, that we have something that is, we have multiple possibilities. We have an or, yeah? So in this case, if we have Vito Young is a Godfather, then we know that Vito Young is the same as Vincent, or the same as Michael, or the same as Vito. And that's not so easy to write down in a rule. So a finite set of rules may not be able to define everything we need in OWL, is the point. So we can't really just define it using rules like we've seen in RDFS and in other cases. So how can we begin to formally define what classes mean, is the question. Yeah. So any ideas? how we could formally define what classes mean? So what does it mean to formally define? Essentially, we're going to have to define classes and the meaning of this sort of definition based on some existing formalism. Does this look like any other existing formalism you might have seen? Any existing language? Yeah. Induction? No, we can use induction to prove properties, but for the definition, not necessarily. Does it look like anything from maths, from mathematics?
Okay.
Sets. Yeah, we can define these things based on sets. Yeah. So we already have an existing formalism for sets. We already have an existing theory for sets. So we can define classes based on some sort of set theory. Yeah. So we can use set theory. So how does this look? If this is set theory, then we can say that there's a set of individuals or elements like Vito, Michael, Vincent. Yeah. So we need to be a little bit careful and distinguish the person from the identifier. So here we're really talking about the entities, the people, yeah, in this case, or the building or the movie, what have you. We have a set of classes like the Godfather, yeah. And we have classes mapped then to sets of individuals. So Godfather represents a set of individuals is the main notion here. So Godfather maps to these three instances here. And that precisely defines what this axiom is saying. This axiom is saying that this class refers to a set, and that set has precisely these three elements here, these three people. Yeah. And that's exactly what we want to say. So names map to individuals then, like Vito maps to this person or character in the real world. Other names might map to classes. For example, in this case, Godfather actually maps to this other type of entity, which is a class, and that class refers to a set. So what about properties? So if we use sets for classes, what will we use for properties is the question. Yeah, so we have this sort of inference here, like we saw in the last class, where sibling is a symmetric property and Connie is a sibling of Fredo, then we can imply that Fredo is a sibling of Connie. Yeah. So how could we begin to formally define what properties mean? We can again use sets. Yeah. But this time a class, if a class refers to a set of individuals, a property will refer to, will map to a set of pairs of individuals. Yeah. So there is a set of individuals, and we have classes mapped to sets of individuals. We've seen this already. There's also a set of properties. So like this real world relation that we call sibling. Yeah. And this these sorts of properties can map to sets of pairs of individuals, like sibling relation in the real world maps to pairs of individuals. Yeah. So for those who are brothers and sisters, it would be you and your brother, you and your sister and you, your brother and you would be pairs in this property, in this relation. So names map to individuals, classes, and or properties. So as before, now we have a new type of thing. We can have a name for a relation or a name for a property. So we have names for classes, names for properties, names for relations, names for individuals. Yeah. So this is a good start. We now have a way to root our definitions or ontology language in an existing formalism, which is set theory. Yeah, and that's the kind of basic notion that we're going to dive into in a little bit more detail now. Any questions or doubts? All good? Okay, so when we start talking about things using set theory, often we have to talk about a universe. So we have to somehow model a universe. So here's the universe. Are we going to model the universe in set theory? We're going to define the universe as a set of everything U. This is called the universe. Great, we model the universe. Universe is a set. So what is in this set? It can be a bunch of stuff. We can have people, we can have countries, we can have classes, we can have whatever we need. It's the universe of discourse. This is called the stuff that we might like to talk about. What about classes and properties? Well, classes and properties, as we saw before, would refer to subsets of U. And properties refer to sets of pairs from you. Yeah, so we could say that a property might relate these two people here, might relate Fredo to Vincent, might relate Fredo to Italy, for example, whatever the properties we might want to choose. Yeah. The next thing we need to model, this is sort of our domain of discourse. This is what we want to describe. Yeah, this is what we could consider to be the real world. The next aspect we need to consider is the data themselves. Yeah. So not just the things we want to describe, but what we use to describe them, which is the vocabulary. So these are the things we use to name and describe things in the universe. So we have a vocabulary, normally IRIs. I'm going to simplify a little bit here and just consider IRIs. So we have a set V, which is our vocabulary with which we can refer to things and name things. We have triples in RDF, which is V times V times V, which is just a set of triples of terms. Yeah. And we have a graph, which is a set of this is the set of all sets of triples. Yeah. So a graph is essentially something, it's a set of triples. Yeah, a set of triples where every triple has 3 terms from the vocabulary. How do we relate the data to the universe is the next question we need to solve. So for this, we have our real world, which is U, our universe, and we have subsets of U, which are classes, and we have pairs, a set of pairs, which would be a property. And we have our vocabulary, and we need a way to map the terms from the data to what we're describing, and that would be the interpretations. So an interpretation of a vocabulary, I here, of vocabulary V, is we need 4 elements to interpret a vocabulary and map it to things in the real world. So we have U, I, C, and P. And U we've seen already. So U is the universe, it's the set of everything in this interpretation. It's essentially all the things that we can talk about in this particular interpretation. We have, here's our example I again, where we have all the things we might want to describe the real world entities, relations, classes we might want to describe. We have I, which maps a vocabulary term to an element of U. Yeah. So what does this mean? It means, for example, we take this term Mary that we use in our data, and I will map Mary to somehow to say that this term Mary refers to this real world person. Yeah. We have I, which maps Fredo to the real person, Vito maps to the person, and so forth. We have Italy, Oscar, and Sonny. Yeah, so we imagine somehow that these terms we use in the data map to real world entities and real world things. We have C, which maps a vocabulary term to a subset of U. So we have, in this case, we have some of our vocabulary refers to classes. And this C function, what it will do is map essentially it will map a class term to a set of individuals that refers to it. Yeah, so we'll take this term person in our data, and this interpretation C will tell us that actually this is referring to a set of individuals, and here's all the individuals, and we can interpret that or understand that as mapping to all the people. We can also have another set Godfather, and this will map to the set of the individuals in our data or in our interpretation that are godfathers. Finally, we have P, and P maps the vocabulary term to a set of pairs from U. So we have P parent, for example, which will map to pairs such that the first element is a parent of the second element. Yeah, this is the interpretation of what this means, what these properties mean. So we have 4 elements in our interpretation of a vocabulary. We have the universe, the things we want to talk about. We have this I function, which maps from vocabulary terms to elements of U. We have C, which maps from vocabulary terms to subsets of U. And we have P, which maps vocabulary terms to sets of pairs from U. Yeah. Okay. Any questions or that's kind of abstract? We'll get to see soon how we define all the stuff we saw in the last class using this notion of interpretation. So how do we interpret data graphs and not just terms is the next question. So here, all we're doing is taking one term, which might be an individual, a class, or a property, and mapping it to something in the universe. How do we interpret triples in our data? So here we're getting to something called model theory. This is model theoretic semantics, and this has been used to define, for example, first-order logic, description logic, predicate logic, all sorts of things. And it's all based on this idea of using set theory to define formally what these logical languages mean. So a model, we're going to use a model to somehow fit a graph. It's something that's going to describe a graph. Yeah. So a model, in this case, we're going to take an RDF graph, which uses vocabulary V. So G is a set of terms. Yeah. So we have an interpretation I, which is an interpretation of vocabulary V. Okay. So it says nothing about the graph. We're still just have an interpretation of V. And we're going to start to define the meaning of our graph using the interpretation. So we're going to say specifically that this interpretation I is a model of G if and only if the following conditions hold. So what's the first condition? The base condition is that if we have a triple SPO in G, then the interpretation of S, interpretation of O must be in the interpretation of P. Yeah. So the things that we refer to from by S here, which is a vocabulary term, and the thing that we refer to by O here, this pair must be in the set of pairs corresponding to P. Yeah. So this is our base interpretation, our base definition. What's nice now with all of this setup, all this mathematical setup, we can define pretty much anything we want. So how do we define the semantics of types is the next question. So what this would say is, if we have a semantics of types, if we have S type O in G, what would we expect here? So if we have, if S or yeah, type O is in G, then what would we expect? So we would expect something about the interpretation of S. The individual that we refer to by S should be in, yeah, C of O. Yeah. So the individual what we refer to by S should be in the class that we refer to by O. Yeah. So this is what this looks like here. So if okay, in this case, rather than putting directly the condition of the graph like I did on your board here, we're using the condition implied here. So if the individual referred to by S and the individual referred to by O are in the relation RDF type, then this means that the individual S must be in the interpretation of the class. Yep. What about subclass? So let's try again. Let me see if we can make this one. That's right. The way it's on the slides better. Although it's equivalent. So if ISIO is in the property interpretation for RDFS subclass of, then what do we write? Yes, yes, yeah. So the class we subset are equal to CO. Yeah, makes sense. So the class we're referred to by S must be a subset of the interpretation of the class that we referred to by S must be a subset of the interpretation of the class that we're referred to by O. Yeah. Yep.
I don't know the last two properties are related with the graph.
So these last two properties here are related to the graph, right? So if we say that S or the F type O in the graph, then this implies that S type O must be in the interpretation. And then this gives us these definitions here.
But the left side is not equivalent
Yeah, so we have, actually, I removed those slides, but in some cases, we can also, if we infer, there's two types of semantics. There's an if semantics, if then semantics, and an if and only if semantics. So there's another semantics which will also give you the relation in the graph. Yeah. So actually, I removed that during the pandemic to create the class shorter, but in the PowerPoint, you'll see the difference between those. Yeah. So this is a particular way of defining it, which is if then, but in other cases, we can define it as if and only if. So it means that if some semantic condition holds like this, then we infer also in the other direction. Yeah. So that's stronger. That's a stronger semantics. That's a good question. Semantics of subproperty. We can do one more. So we're gonna have sub property of, and we're going to change this. We're gonna just remove this. So what would we say in this case? So we would say that the set of pairs of individuals referred to by S is subset or equals, yeah. The set of pairs of individuals referred to by O. So it's quite similar. Yeah, so it's still a set, right? It's like it's a set of things. So we can say that the set of pairs here is a subset of the set of pairs here. Yeah. So if let's say S were brother of and O were sibling of. Yeah, so it says that all the pairs that are in the brother of relation must also be in the sibling of relation. Yeah. Okay. Semantics of domain and range. We'll just put that on the slide. So I have a little trick here, or a little notation trick, because otherwise we need to write it out with first order logic or something. Yeah. So okay, so what we say here is if we have S domain of O, then what we want to say is that the first elements, all the first elements of the relation P must be within the class referred to by F. Yeah. And in this case, we use the two. We say that the second elements must be in the class. Yeah. We could write it out more explicitly in other ways, but this is more convenient. Okay. I'm not sure I pointed that correctly, but let's see. Okay. So we're going to continue kind of rapidly. We're not going to go through, we're going to go through a number of features just to get a feel for some more features, because thus far as well, we've only seen RDFS. So how does it work for OWL? It's the same idea. Yeah. So what about OWL semantics? How do we define the semantics of same as, different from? So if we say that IO is in P of OWL same as, what does it tell us about S and O, IS and IO? It means that they're the same. They're equals. Yeah. So here we see if we know that S and O are in the same as relation, then it means that they must be referring to the same individual. Yeah. IS is equal to IO. In the different from case, if IS and IO are in the different from relation, then it means that IS cannot be equal to IO. Yeah. Inverse properties. If we have IS and IO in the inverse of relation, what does it mean? It means the following. Yeah, so you probably get the idea. So for all XY that are in the property S, for all XY, then XY is in the property for S if and only if YX is in the property for O. And the if and only if gives us in both directions. Yeah. Transitive properties is something similar. So we're going to have XYZ this time. For all XYZ, if XY is in the property for S and YZ is in the property for S, then it implies that XZ is in the property for S. Yeah. Disjoint classes. If S and O are in the relation disjoint with, for classes, what does it mean? It means the intersection of CS and CO is empty. Yeah. So if we say that S and O are disjoint classes, which means that they have no individual in common. It means that their sets must be disjoint, which we write by saying that their intersection is empty. Yep. And so on. Yeah. So we could continue defining the rest of the features we saw. You can imagine it wouldn't be too difficult, yeah, to write these conditions out. So this gives us a formal, an exact formal definition of what the language means. And we're relying on some existing formulas, in this case set theory, in order to formally define what each of these sorts of axioms mean. Any questions or doubts about this? Okay, so this is a model. I is a model of G if and only if, and then we have these conditions here, these semantic conditions here. So a model essentially based on this is any world that an ontology might describe. Yeah. So it's somehow an abstract representation of what our ontology is describing, one possible world which our ontology is describing. So here we have an ontology in orange, and it says has daughter is a subproperty of has child. Has child is a subproperty of ancestor of. Ancestor of is a transitive property. Carmela has child Michael. Michael has daughter Mary. And here we have our RDF graph representing the graph and some other relations. So as a model, we're going to consider an interpretation like this, where we say that I, Carmela, is this person here, that I, Michael, is this person here, the interpretation of Michael, the interpretation of Mary is this person here, the interpretation of this property is this, this relation here, the interpretation of Haschel is this, and this is the interpretation of ancestor of, yeah. So the question then is this model that we've represented here, is this a model of this ontology or not? So essentially, in this case, we have to see somehow if this is a possible world that this ontology could be describing, yeah? Which means that it needs to be somehow complete, yeah? So what do I mean by complete? Essentially, if there's something, in this case, for example, Carmela is not noted to be the ancestor of. So if in the real world, Carmela was not the ancestor of Mary, yeah, then it means that there's something weird here, because we have Carmela, ancestor of Michael, Michael, ancestor of Mary, and we've said that ancestor of is transitive. So if it doesn't hold in the world that we're describing, that Carmela is an ancestor of Mary, then there's something wrong here. This doesn't fit. It's not a model of our ontology, yeah? So in this case, is this a model of this ontology? We're going to say that no, it's not. It's not a model of this ontology, because in the real world, in our interpretation, in our talking about entities and relations, real world things, if Carmela is not the ancestor of Mary in the world we're describing, then it's not compatible somehow with these definitions. We shouldn't define that ancestor of as transitive property. So no, since Carmela needs to be an ancestor of Mary. Yeah, so if Carmela is not an ancestor of Mary, then this ontology doesn't fit with this world we're describing. Yeah. Again, because we have Carmela ancestor of Michael, Michael ancestor of Mary, and we've said that ancestor of is transitive. So now we have a model of the ontology. If we add this Carmela ancestor of Mary, then this is essentially something that this ontology could be describing. Yeah, this could be a configuration that the ontology describes. Okay. So what about in this case? What happens if we add some more information, or we have some other relations in the real world, like that Mary likes cake? Yeah, is this a model of an ontology? So if we look at our ontology, we don't even mention cake anywhere. We have no idea, we have no way of knowing that that Mary likes cake. So is this a model of the ontology? The answer is yes, this is a model of the ontology. And the reason for that we spoke about in the last class, because in OWL we assume the open world assumption, which means that we assume that the data are incomplete. Yeah. So it means that essentially a model can have more things in it that are not captured or described by the ontology. Yeah. So in this case, we see that Mary likes cake. There's no problem. We can have more real world relations and entities not described by the ontology. So it can still, this would still serve as a model of the ontology. Okay. This is very conceptual. Yeah, we're going to get to the formal definition soon, but what this allows us to define are certain reasoning tasks. So what is the use of these models? Essentially, it gives us a way to define very complex types of inference. So what happens is when we add axioms, we remove possible models. Yeah, at the start, anything is possible. We could be describing any sort of world. But as we add more data and more axioms, what we're doing is we're chiseling away the possible models. Yeah, we're removing the possible models. So at the start, when we say nothing, almost any world is possible. Yeah, or any world is possible. If we add axioms, fewer worlds are possible. So it's similar to this idea, this sculptor, this famous quote from the sculptor, Michelangelo Buonarroti, I guess, I don't know. The idea, the quote states that the sculpture is already complete within the marble block. Before I start my work, it is already there. I just have to chisel away the superfluous material. So it's similar when we're defining ontologies. We're going to have all the possible models, and as we start adding more axioms, we start chiseling away from the block or removing models that are possible. Yeah. So as an example, just to go back here, in this case, for example, this model would be completely valid if we removed one axiom. What would that axiom be? Yeah, transitive property. So when we add that transitive property axiom, what do? We remove this model as a possibility. Yeah, so we add an axiom, we remove possible models. Yeah, that's the idea. Okay, so as we add axioms, fewer worlds are possible. Yeah, so we start with all the possible models and then we start moving them. Yep. So the universe can be anything. Yeah, so the question is, how do you define the universe in this case? So we're never in the computer, the idea would be to have a computer representation of knowledge. Yeah, so the computer will never know about real world people, it will never know about movies. But it doesn't matter. What we're going to do is define something at a very high level. And we're going to say if there exists any model possible, then something will hold. Yeah, we'll see that soon in terms of entailment. So what it means is essentially the universe doesn't really matter. It's just more like a conceptual idea. Yeah? And then we're going to say if any universe exists or any interpretation exists with these properties, then something else holds. So it doesn't really matter what the universe is. So the universe is a set. Yeah. So the universe is like the set of all the individuals, all the things we want to talk about. It's the universe of discourse. Just a plain set. Yeah. We cannot describe no, exactly. Yeah. So the when we look at the slides with these examples here, it's to give some intuition, but really the exact values in the universe, it doesn't matter, because we're going to say that there exists an interpretation, and then it's more about the structure of the model or the structure of the interpretation. It's not really about the elements. So that's one aspect some people are critical about. They say, well, your IRI, you can map it to anything. It doesn't have to map to what people, think about in the real world. But there's no way, I can see anyways, there's no real way in which you can actually define an interpretation that's meaningful, as in like saying that this really corresponds to this real world person. It's not even really clear what that means. So when we use later interpretations, we're going to say that there exists an interpretation, for example. And then we don't really care about what the U is. It can be whatever points we construct. So what matters then is just the structure of the interpretation. Yeah. So what this means here is it basically, in this case, yeah, we have these nice pictures of the actual people that it refers to, but in the real world, or not in the real world, but in the mathematical formalization, it really doesn't matter what these things are. It's more that there exists some element in the set that can satisfy some conditions. Yeah. So we can never enforce this mapping that Mary maps to the Mary we want it to map to, or that we consider. Yeah. But we can still reason about the data. If we apply these interpretations ourselves, if we give meaning to what this Mary IRI refers to this thing here, then we can manipulate the symbols using the logic, and then at the end we'll have more facts that mention Mary, and we apply that interpretation when we look at the data. Yeah. So, any more questions? Okay. Yeah. So, one of the main relations that we want to define for ontologies is what ontology follows from what other ontology. What ontology follows logically from what other ontology? Yeah. So here we have an ontology in O in yellow. We have another ontology O prime in blue. And the question is, does this blue ontology follow as a necessary consequence of the yellow ontology? Yeah. So let's have a look. We can look claim by claim here and see if it follows. So we have Michael, Hasper, and Carmela. Does that follow from this ontology? Yes. Yeah, because we have Carmela has child Michael and has child inverse of has parent. Yep, so that we're good. What about this next one here? Michael has child Mary. Yep, and we have has daughter subproperty of has child. Yep, and Carmela ancestor of Mary. It's a little bit more tricky, but we can get there. We have ancestor of a transitive property. We have has child subproperty of ancestor of. So we have Michael has child Mary, so that means Michael ancestor of Mary, and we have Michael has parent Carmela, so that means Carmela has child Michael, which means Carmela ancestor of Michael, and that means eventually Carmela is ancestor of Mary. Yeah. So okay, we can get there eventually. Yeah, but we have enough to entail this as well. So there is an entailment. In this case, we have this entailment, and how we define this in terms of models, what we saw before, we can formally define this based on all the stuff we formally defined before, by saying that any model of O is a model of O prime. Yeah, and this is a key aspect that's kind of strange, but if we can grasp that, then we get the idea, right? So this is not so easy to get at the start. It basically states that this ontology, yeah, states nothing new over this ontology. It gives us no new information. Yeah. How do we know it gives no new information? Because the set of models it permits, yeah, is larger than the set of models this permits. It's more specific, right? So the more specific we are, we start ruling out models. Yeah. So essentially, if every model of this thing here is a model of this thing here, then it means that we've not really added any new information. We've not chiseled away any models or anything extra. So basically, any possible model of O is a model of O prime. This means that O entails O prime. It means O prime says nothing new over the original ontology O. Okay. So, or we could say it another way, that O prime has a superset of the models of O. Yeah. So this formally defines our entailment relation. O prime says nothing new over O. So this is a kind of a strange thing, because, you know, it seems that if this has more models, then it has more information. But again, it's the inverse relation holds. Yeah, more information means fewer possibilities, fewer models. So this is the entailment symbol that we use. So this means that this ontology entails this ontology here, which means that this is a logical consequence of what we stated along with our definitions in the previous ontology. Do we have an entailment here? Does O entail O prime? Does the yellow ontology entail the blue ontology? No, we have no way to know that Mary likes cake. So does O entail O prime? No, there are models of O that are not models of O prime. Yeah. So in this case, we have a model of the yellow ontology, but we have, this is not a model of the blue ontology. Why is it not a model of the blue ontology?
Well,
well, yeah, well, for what reason? What are we missing? Yeah, so we don't know if Mary likes cake in the world we're describing. Yeah, so Mary has to like cake in the model in this world we're describing, for this to be an accurate reflection, for it to be an accurate description of that, for it to be a model of that RDF graph. So this is a model of this ontology here. It's not a model of this ontology here. This means that this ontology here is not a logical consequence of this. It means that this ontology adds something new that we've not seen before. What is the new thing? It adds that Mary likes cake. Yeah. So this is an example in the other direction of when an entailment doesn't hold because there are models of this ontology. Sorry, there are models of this ontology here that are not models of this ontology here. Yep. So Mary doesn't like cake for some reason. Hard to believe. Yeah. Any questions, doubts? No. Okay, so we're going to look at 3 reasoning tasks that are commonly defined. Actually, there's a lot of them. There's 7 or 8 or 9 or 10. I don't know how many. There's lots of different reasoning tasks that people use. So the idea is you've defined your ontology. You've gone into a certain domain. Maybe you're in the biomedical domain and you've gone and you've defined what different diseases mean, what different treatments mean, what different treatments should not be taken together. You've defined all this formally. You've used something like an ontology language like OWL for this. And the question is, now, great, what can I do with this? Yeah, so what kinds of tasks can I solve with this ontology? So we have different types of reasoning tasks. The first type of reasoning task is what we've seen in the labs, and it's called materialization. Yeah. It's the first thing you might think of. I have my ontology, and now I want to know what follows from it. Yeah, give me all of the conclusions I can get from this ontology. So this is precisely what you've seen in the labs. Yeah. So you give your axioms, you give your data, your axioms, your definitions in RDFS or now, and then you say, okay, press a button, give me the full graph, give me the stuff that also follows as a consequence. So materialization just means writing down the entailments. So based on this ontology, we can start to do some reasoning, and we can say, okay, Michael has parent Carmela, holds, Michael has child Mary, holds, Carmela has ancestor of Mary, and so forth. Can anyone see any problems with this particular task?
Writing that one than we are actually.
We're writing a lot more than.
We're actually comparing.
No, so in general, we can program this so that everything here is sort of entailed, so that whatever we materialize here, the result will be entailed from this ontology. We can do algorithms that are okay that way. The problem is rather in the other direction. Yeah, we can't write down everything that holds because it can be infinite. Yeah. And the reason why it can be infinite is because, for example, here we say that a person is equivalent to the class of things that have exactly 2 parents that are people. So what does that mean? So it means Mary is a person. So what does a person need to have? 2 parents. And those 2 parents should be persons. So those parents are persons. What do those persons need? 2 parents who are persons, and we can start to create through blank notes, for example. If we use blank notes to represent that something exists here, as we do in RDF, then we can start to create an infinite number of entailments. Yep. So this is on the data level. On the more conceptual level, we can also say that if person is equivalent class to qualified cardinality 2 and property has parent on class person, then we can say that person is a subclass of the things, a subclass of this, okay, of this definition here. And we can say that they're a subclass of all of the classes where we just start incrementing 2 to 3 to 4 to 5 to 6. Yeah. For max qualified cardinality. Yeah. So if somebody has 2 parents, it means that they also must have at most 3 parents. They must have at most 4 parents. Yeah. But subclass, not equivalence, right? So if you have 2 parents, exactly 2 parents, it means you're also in the class that has at most 3 parents, at most 4 parents, and so forth. So we can get these sorts of infinite number of subclass axioms in this direction, and so forth. So we can do materialization, but we can never write down everything. So the stuff we're using in the labs, we're never going to be able to write down everything that holds. Yep. So we can write out stuff that definitely holds. So that side is not a problem. So everything that we write down will be entailed. The resulting materialized graph will be entailed, but it won't be everything that follows from the original ontology. Okay, second task that we have is called satisfiability. And this has been used, it's used in general in ontology design and engineering, just to check to make sure an ontology makes sense. It's also been used to check the internal consistency of different sorts of domains. So it's been used, for example, in law, where you define your law using something like an ontology, and then you see if the definitions are internally consistent or not. So what is satisfiability? It asks, does O have a model? Yeah. So essentially it's asking is O consistent? Yeah. So an inconsistent ontology, an ontology that contradicts itself, has no model. Yeah. So does O have a model? So in this case, we have person is equivalent class, qualified cardinality 2, on property has parent, on class person. So we're saying a person is equivalent to the class of things that have two parents that are people. Okay, probably biological parent would be better, but okay. So anything wrong with this? Would this make sense? Let's say it was more biological parent as well. Any exceptions? Animals? Maybe it's going in that direction.
Creo que hay un caso de una persona que tiene tres padres biológicos.
Ah, is it?
Sí, porque el ADN mitocondrial está tomado de un donante.
Ah,
Entonces, si revisan su ADN, le funciona para ver ADN de su papá, su mamá biológico, y de un donante mitocondrial. Entonces, tiene tres padres biológicos.
okay. I haven't heard of that case, so that's another problem. That's another problem. So people can have more than two biological parents. So this is this. If we think about what we're saying here, actually it's not necessary, but what we're thinking about when we say this is an infinite chain of people. But that's not what really happens, right? So at some stage there was a person whose parents weren't people. Yeah. Okay, so there was at some point in evolution, right? It's not like humans were the first life to form, and even then, I mean, even if they were the first life to form, then that first human had no parents, right? So, okay, so what we're going to do is we're going to describe a first person, the first human. Yeah. We're going to say that this first human, qualified cardinality 2 on property has parent on class 8. Now, biologically speaking, we're going to have to take some liberties because humans are apes as well, kind of, and so forth. And but okay, we're going to take a few liberties here, yeah. So we're going to say a person is qualified cardinality 2 on property has parent on class person. And we're going to have this definition of a first person, and we're going to say that this first person is also a person. It has qualified cardinality 2 on property has parent on class 8. It has two parents that are apes. Yeah. So we define this ontology, and now we want to ask: is this consistent? Can this describe any possible world? Yeah. If it can't describe anything consistently, then it's inconsistent. Yeah, it's just there's something. If there's no world we can describe, then it means that the ontology is inconsistent. So what do we think? Do we think that this ontology is satisfiable? Do we think you can have a model? Do we think it's consistent? No, we think it's not satisfiable. It is. It has a model. So what is the model? Let's start with this. Yeah. So we have here a model where we have the first person. And this first person has parent A and has parent B. We don't know what the parents are. These are existentials. And we're going to say that parent A is of type person and of type ape. And we're going to say that parent B is of type person and of type ape. Yeah, so both the parents are of type person and of type ape. Is this somehow coherent, consistent with the ontology? Yes. Well, so we've never said that person and ape, something cannot be a person and an ape at the same time. So what we've done in the case of the first person, to make it compatible with the definition for person and the specific definition for first person, we've said that their parents, they have two parents, yeah. Both of their parents are both apes and persons. Yeah. So we satisfy this condition here. Yeah. So first person is a person, and it has two parents that are persons. Yeah, A and B are persons. And we've satisfied this definition here because we said A and B are also apes. Yeah, so that's fine. There's nothing stopping us from that. Intuitively, we might say, okay, person is disjoint from ape, but we've never actually defined that, right? So this is still consistent. There is still some possible world that this describes. So yeah, not shown here. There's more elements we would need to add to the model. That there's parents of these parents here would need to have their own parents and so forth. So it's infinite, so we can't put everything. So what could we add to this to make it unsatisfiable? What could we add to this ontology if we can still, have models? If we still have worlds that we can possibly describe, what would we add to stop this sort of example? Any ideas? Yeah, perfect. So person disjoint with thing. Yeah. So we're gonna say now we're gonna block this this sort of model by saying no, something cannot be a person and an ape at the same time, which is probably biologically incorrect. And some people might consider humans to be apes, right? But we're gonna say ape disjoint with person. And we're going to ask again, does O have a model now? What do we think? It has a model? Yeah. What's the model? How do we construct it? Or maybe it doesn't have a model. I will give a hint that there is a model. It's still satisfiable. What is this model? We're saying that a person has to have two parents that are people. We're saying that the first person is a person and has two parents that are apes. And then we're saying ape disjoint with person. So we can no longer, this first person can no longer have two parents where they're both ape and human. Yeah. But we've never said the first person has to have two parents. Yeah. We've said that first person has to have two parents that are people and two parents that are apes, but we've never said that they had two parents overall. Yes, we've just said specifically two parents in the class people, two parents in the class ape, and we never gave an upper bound for parent. Yeah. So the qualified cardinality only counts, it completely ignores anything not in these classes. Yeah. So what does this mean? We have a model where the first person has four parents. Yeah. So we have a model where the first person has four parents. Two parents are of type ape. Two parents are of type person. And this is a model of, okay, we need to expand it with the stuff, these guys also need parents and so forth. But this is the basis of a model for this ontology. So the ontology O is still satisfiable. And again, just not shown. There's a bunch of stuff here that we would need to add to make it a full model, but it's the basis of the model. So we have in our ontology allowed this sort of case where first person has two parents that are apes, two parents that are people, and this is completely compatible with everything we've described here. Okay. So what would we need to add to this ontology to make it unsatisfiable? What would be the next thing? We could say, for example, first person has two parents without the qualified part. Yeah, just cardinality two. So what would we need to add to make to O to make it unsatisfiable? If we added that person as a subclass of cardinality 2 and property has parent, but all people have at most two parents, now we can no longer construct a model that fits the ontology. Yeah. So this ontology no longer has any models. Yeah. It means essentially we've adding this to the ontology, we can't possibly describe anything, and it means that this first person cannot exist according to our definitions. There cannot be a first person who satisfies these constraints. We could say that all of the parents of people are people. That would also do it, because it would force in the four parent configuration that the apes must be, all of the parents are people, which will not be possible. Or we could say that first person is an ape, because if ape and person are disjoint, then saying first person an ape or first person a person would also make it unsatisfiable. We could say that first person is an instance of the class owl nothing, which is used for the empty class and owl. All these sorts of things would make our ontology unsatisfiable, yeah, where it has no models. Okay, and there's probably a bunch of other stuff we could add. So an unsatisfiable model, an unsatisfiable ontology cannot model any world. It is inconsistent, and this is the case of the world imploding that we saw earlier. Okay, so in terms of entailment checking, does O entail O prime? Yeah, sorry. So what happens if an ontology is inconsistent? What's this whole world imploding thing? So in logic in general, there's this idea that anything follows from a contradiction. I'm not sure if you've heard that before. Yeah, so anything follows from a contradiction. So if you assume a contradiction, then you can infer whatever you want from that. Yeah. So what does that mean? It means essentially that, let's say this was inconsistent here. Yeah, this ontology O was inconsistent. I don't think it is, by the way, but let's assume it worked. If this ontology is inconsistent, then what models does it have? None. It has no models. Yeah. So if this has no models and our entailment is defined this way, are all models of O prime 2. So we have our all models of O, which is the empty set. Yeah. Models of O prime 2. It means that if this is the empty set, if this has no models, if it's inconsistent, then it entails any ontology. Yeah. It's the most specific we can get, where we've just completely demolished all the stone and there's nothing else left to do, right? So we removed all possibilities. There's 0 possibilities. So when there's 0 possible models, it will infer whatever. Yeah. So this is why anything follows from a contradiction holds in this model theoretic sense. Okay, any questions about that? Yeah. So we have 3 tasks. We have 3 main tasks we're talking about here. There are other tasks used in practice. We have the task of materialization. We have the task of entailment checking, and we have the task of satisfiability checking. Okay. So we're moving on to reasoning. So the question then is, how can we perform reasoning? So we want to actually write it down a computer program that will check these entailments. Okay. So how do we do this? How do we implement this stuff? What we do is essentially we can reduce entailment down to unsatisfiability. So what we can instead ask is, if we add to O some element of O prime, if it's unsatisfiable, then it means that O entails O prime. So it's this thing of, if we negate this and we say Michael has not shall marry, we add it to the yellow ontology and we check, is that unsatisfiable? If that's the case, it means that O entails O prime. Yeah. So what we're doing here is we're saying so if O follows as a logical conclusion from O prime, it means that something in O, if we negate it, must contradict O. Yeah. So in this case, what it means is we take this ontology O and this ontology O prime. We negate the fact, the only fact in this case, of O prime. We add it to this ontology O, so this is now our new ontology extended, and we ask, is this unsatisfiable or not? So what do we think? Would this be unsatisfiable? So we have has daughter, so property of has child, Michael has daughter Mary, and then we're saying Michael does not have child Mary. Does that make sense? No. So this is inconsistent, it's unsatisfiable, and because it's unsatisfiable, it means that this entailment was told here. So we can reduce entailment to unsatisfiability. So we only have to worry about trying to implement unsatisfiability. Yeah. So the question then is, how do we implement unsatisfiability? Yeah. So there's this quote here from Audrey Hepburn, who said, "Nothing is impossible." The word itself says, "I'm possible." Unfortunately, as computer scientists, we know that she's wrong. There's definitely impossible things. And one of those is implementing a method for undecidability. Doesn't exist. Yeah. So for OWL, for what we saw, for the language we saw. So undecidability, what do we mean by undecidable? You've heard of undecidability before? I guess, maybe. Undecidability means there exists no algorithm that implements this problem. Yeah, let's addresses this problem. So this is an example of, well, a problem that is not known to halt or not. Yeah. So have you heard of the Collatz conjecture? Yeah. So the Collatz conjecture is basically the question of, will this program stop for any input? Yeah. What's the input? It's a number. Yeah, it's an integer. Okay, we have to assume here that it's not just the ints, but also it's whatever size of integer. Yeah, it can be larger than an int. Yeah. So an integer in the mathematical sense, not in the Java sense, but okay. So because we could otherwise brute force this. So what does the program do? It accepts an integer, it prints out the integer n. If n is equal to 1, we return. Yeah. If n is even, then we return Collatz n divided by 2. So we divide n by 2 and we call it the recursive part. Yeah. Otherwise, if it's odd and it's not 1, then we return 3 times n plus 1. Yeah. So why? Because we can. Why not? Yeah. So the interesting question then is this complete? I'm just after noticing that there's one participant in the Zoom, which is me, I guess. I'm not sure why that is. Okay, I'm not sure. Maybe something happened with the connection, but okay, yeah. We're recording anyways. So in 6. Yeah. So what would we pass if we pass Collatz? If we pass 6 to this function here, what will be the next value that it gives us, that it will print? 3, because it divides by 2 because it's even. What does it give us for 3? 10. Okay. And what does it give us for 10? 5. 16. Yeah. So once we reach a power of 2, we go straight to 1 and we finish. Yeah. So our goal is somehow to get to a power of 2. The question then is, will this program terminate for any input integer? And nobody knows. This is an open problem. If we, of course, we can brute force it up to a certain point, but will it return for any integer? And of course, it returns for all of the integers we've tried, because if not, we would know, right? If we have one counter example, then we know. So this is an open question, whether or not this program terminates for all inputs. So does this Java program terminate on all possible positive inputs is the question. And we don't know. Yeah. So this relates to a problem of undecidability, an undecidable problem. Yeah. So the Collatz conjecture is an unsolved problem in mathematics. If we knew that this program terminates or does not terminate on all natural numbers, this problem would be solved. Yeah. So this is the Collatz conjecture. So what is this is from XKCD. The Collatz conjecture states that if you pick a number and if it's even, divide it by 2, and if it's odd, multiply it by 3 and add 1, and you repeat this procedure long enough, eventually your friends will stop calling to see if you want to hang out. Okay. So we don't know. So this relates to the halting problem, which is if we could solve the halting problem, we could solve the Collatz conjecture, at least in theory. So the halting problem, have you heard of the halting problem before? No? So this is the classical undecidable problem in computer science. So you're given as input a program and an input to that program. And what you're supposed to output is true if the program halts on that input and false otherwise. Yeah. So you're given some program, some C++ code, let's say. And you have to develop some other program, let's say in C++. So the C++ program you need to implement should take any C++ program and should say whether or not it will halt on any of the valid inputs for that program. So is that possible? This wasn't known to be possible or impossible until the 30s or 40s, I guess, when it was proved to be undecidable. So a general algorithm to solve the halting problem does not exist. So it will not hold for all program input pairs. It might hold for some program input pairs. So we'll see some problems, undecidable problems soon. Why is this the case? So the idea is a kind of a brief sketch of why we cannot never program this thing in C++ that accepts another C++ program and says whether it will terminate or not on all inputs. Why we can't have such a general procedure or a general program is the following. Yeah, so let's assume that this halt function that we could implement this halt function. Yeah. So let's assume that we could in C++ write a program that takes some other program and says whether it will halt on any input or not. So we're going to call that function halt. Yeah. So we have this function halt and we're going to create another program. And what's this program going to do? It's going to cheat. Yeah. It's going to prove somehow that this halt cannot work. So what this program does is it asks the halt function, will I halt? Yeah. So I'm the function, the cheating function. I ask the halt function, am I going to halt? Yeah. And if it says yes, what do I do? I continue forever. Yeah. And if it says no, I won't halt, what do I do? I halt. I stop. So I just contradict it. So there's no problem. And the algorithm I've written is still an algorithm. I'm just calling this halt function, yeah, which is fine. If halt were a function, then calling it as part of a function is perfectly normal, yeah. So this is a sketch of the halting problem proof. This is essentially the whole argument, but there are some details about passing myself to the halt function that is normally the way it's done is I create a copy of myself and then I send the copy to the halt procedure. But this is the core idea, yeah. So I have a procedure and this cheating procedure. Basically, I ask halt, am I going to stop? If halt says yes, then I don't stop. If it says no, then I stop. I just contradict it. And the fact that I can generate such a program creates a paradox, which means that something is wrong. Yeah. It means that in this case, we can then show that the halting problem, this halt function could not exist. So this is the halting problem. This is undecidable. This is the original undecidable problem of computer science. So then we have this collapse halting problem. So we have this question for the collapse halting problem. We have the question of given no input, what we want to output is true if the collapse program halts on all inputs and false otherwise. Yeah. So what do we think? Is this problem decidable or undecidable? Or maybe it's not known to be either. What do we think? Hmm?
Undecidable.
So it seems undecidable. Yeah. In this case, however, there's a very specific answer. There's a trick. It's a nasty trick I've done. Yeah. So there are two possible implementations for this. So we could implement this problem just with return true, or we could implement it with return false. One of these is a valid implementation of this problem, right? So one of them is correct. We don't know which, but one of them is correct. So it's decidable, yeah? So the point here that is important to make is it doesn't matter if we know how to implement it. If we don't, so essentially something can be decidable, but we don't know how to implement it, yeah? So that's different. Decidabilities or undecidability really means that no such algorithm can exist. But there are cases where we want to implement something, but we don't know how to implement it. That's different from undecidability. Yeah. So we're going to look at an undecidable problem, which is one I like a lot, and one we're going to relate back to ontologies a little bit later. And we're going to finish with this, and I'm going to talk about the topic of the next class. So we're given as input a set of dominoes, which are these sorts of shapes here. What is a domino? A domino has four things. It has a top color, a bottom color, a left color, and a right color. Yeah. Each domino has that. We have as output, what we want to do, given this input, is return true if there exists a valid infinite tiling, like T, or false otherwise. So what is a valid infinite tiling? Essentially, for our first tile here, we can put anything. Yeah. But the tile we put above it has to be compatible in terms of color, which means we can only put blue beside blue. Yeah. The tile that we put to the right of it must be also compatible in color. Red matches red, and so forth, right? So these colors, these adjacent colors, have to be compatible. Yeah. So let's try a couple of examples. Let's say D is equal to the set. We're going to add green here. We're going to add green here. We're going to add black here and black here. Does this allow an infinite tiling? Yeah, it does, right? So we can just start to do this. And we can continue to infinity, right? So this one is a yes. This would return true given this input. Yeah. What about this case? No. So in this case, there's no infinite tiling possible. We would return false. Yeah. What about if we extend it and add what about this case? Yeah. So we can stack these ones. So every second row, the first row we could choose, for example, this one for the first row. And then the second row, we could choose this one. All the same. And then the third row, we could choose this one, and the fourth row, this one. What about this one? Essentially, we can never use this tile here because we'll never have anything that can go to the left or to the right of it. Yeah. So we can't use this tile here. So then the question is, what about this one? Yeah. And then what if we have yeah. So we can continue. In this case, it would still be no. Because this red, then we can't continue it, right? So if you were to think about it, when you start to get into more and more complex examples, how would you program something? How would you write in Python and C++, in Java? How would you implement this program? Yeah, it wouldn't be easy, right? To return true or false. So we could cover some cases. We could cover some easy cases, maybe easy true cases, easy false cases. But the question is, how can we implement a general procedure to decide this? Yeah, given D, to say yes or no. And we might think about it, and we might work very hard on this for a long time. And we might come to the realization that it's even harder than we thought, because actually it's is this problem decidable or undecidable? This is an undecidable problem. Yeah. So it means that there does not exist any algorithm. Yeah. We can write an algorithm, but it will have one of two properties. Yeah. So we can write an algorithm, but it's possible that it will never terminate for some inputs. Yeah. Or we can write an algorithm that's incorrect for some inputs. Yeah, it returns false when it should return true, or it returns true when it should return false. We can never write a correct algorithm that will always finish. Yeah. Doesn't exist. How do we know this doesn't exist? So there has been, it was proved, these are called Wine tiles sometimes, so possibly by Wine, I don't remember. But essentially that there is a Turing reduction, there is a way to reduce from this problem to this problem, which means that we can represent an instance of the halting problem as if it were an instance of the tiling problem. Yeah. And we can do that with a special or type of reduction, a Turing reduction, which basically means that given an implementation for this thing here, we can write this sort of wrapper function. Yeah. And we could solve the Turing problem if we had an implementation of this problem here. So as a consequence, it must mean that this is undecidable. Yeah. Otherwise, this would not be undecidable here. Yeah. We could just use this to solve it. So thus the tiling problem is undecidable. This is an undecidable problem. We can never have an algorithm that always holds and gives the correct answer for this problem. So what we can do then is we can reduce from tiling to owl entailment. Yeah, so we can actually show that owl entailment is undecidable because this problem is undecidable. So given this D, and the question, does D have an infinite tiling? We're going to be able to reduce this to ontology entailment, where we're going to show that if we could solve entailment in owl, we could solve the tiling problem. And if we could solve the tiling problem, we could solve the halting problem. And we can't solve the halting problem. So it means that we can't solve any of these other problems. So that's to be continued next time. We're going to talk about that. We're going to show how to do this reduction and prove undecidability. So this is not just for OWL, by the way. This refers to knowledge representation in general. So the message we get from this is we can write down all these logical statements and we can get all of these conclusions. But at some point, there is a limit to knowledge representation, where essentially we'll be able to define, for example, open problems in mathematics. Yeah, and ask, is this entailed by this other thing here? Yeah. So at some point in knowledge representation, and it's a lot sooner than one might think, we reach a point where machines can no longer give us the answers. There's no possible algorithm that can actually reason and tell us this information. So machines are limited in terms of knowledge representation. There's a limit in terms of what machines can help us with for knowledge representation. If that were not the case, and that was the origin of undecidability, we could have algorithms that could solve a lot of open problems in mathematics, which is not the case. Yeah. Okay, any questions or doubts about that? So the next time we're going to talk about this reduction, which is it's about 10 minutes or maybe a bit longer, 15, 20 minutes. Then we're going to conclude that, okay, owl entailment is undecidable. And then we're going to talk about what do we do in practice. If something is undecidable, what do we do? And we're going to talk about different types of algorithms and their strengths and weaknesses for reasoning with owl. Reading groups. So it would be a good chance to start with the reading groups. This week, I'm going to publish some more information in the forum. So the task overall would be to find and present a paper relating to the topic of the course. Yeah, so it's a postgraduate course, which means it would be good as well for those. Do we have postgrads here? Okay, postgrad in theory, it's a postgrad course. Yeah. So in any case, for those who are interested or maybe thinking about going on to a postgrad course, it's an important part of postgraduate studies will be when you reach a master's level will be to access research in computer science, to find papers, to read them, to understand them. So we're going to have a first approximation. Maybe, I'm not sure if people here read research papers in computer science. No? So we're going to do that in the reading group. Yeah. So you're going to work in a group of 3. You're going to select a paper that you'd like to present. So the goals would be that, okay, first of all, yeah, you get maybe used to, or you have a first approximation with the research literature. So you're going to find some papers and read them and understand them and present them. The other goal would be to, within the course, to get an overview of the sorts of research topics that are ongoing in this area. So this is mainly a research field. Yeah. So you're going to find a paper of interest to your group related to the semantic web. So we would expect you to work in groups of maximum 3. We'll also, you must work in groups in the sense that we'll do assignments for those not in groups. Conference, you should present a conference or a journal paper in the semantic web area. It cannot be selected by another group, so we don't want 2 presentations of the same paper in different groups. And I will post some more instructions on finding papers in the forum. So this would be Google Scholar, semantic web conferences and journals, whatever it might be. Any questions about that? So we're in week 5. That will be due about week 7, I think. We'll define the exact. Well, no, that might be too short. Maybe week 8 or so. So it will be due roughly around that time. So we'll handle the rest of it by forum. Also, you can propose groups. If you don't propose a group, you'll be assigned one. The other aspect to consider would be if you don't want to do the reading group, you can let me know. So I don't assign you to a group and then you disappear on them, let's say. So I guess most of the people here will probably want to do the reading group. So yeah, so that's the reading groups. After the reading groups, or maybe towards the end of the reading groups, we'll talk about the projects. But the presentation at the end of the reading group will be quite short. It will be a few minutes. Okay. Any questions, doubts? Okay.